Good morning. Really cool to have you all here. I hope your day is going well. I hope you have a great 3-day weekend. And speaking of 3-day weekends, there's no classes at all at Mount Hood Community College on Monday. So if you have classes, my class or anybody's class, make sure you don't show up because nobody will be here. So we have no lecture on Monday. There's no Monday afternoon lab or anything like that. Definitely enjoy the weekend. Now, next week, the only thing technically that's due for those of you at Section L1 is the QA3 lab. And that'll be due Wednesday by 9 a.m. You can turn it in here in lecture. That's fantastic. You can put it underneath my office door or in my mailbox in the science division. Any of these ways are great, but Wednesday at 9, that's the only thing that's due. The following Monday, so a week from this Monday, which I think is June 1st, that'll be the day of our class presentations. So I'm looking forward to seeing those. It should be pretty cool. That'll be the only thing we do on that day. You'll turn in your paper, give your presentation. Any questions, that kind of stuff? All three of you are going to be the benefit today of being here on a day when I know it kind of sucks to come to lecture, but I do appreciate it. A couple times a term, I give out extra credit just for attendance, and all three of you are here, which I do appreciate. I don't hold it against anybody for not being here, that's for sure, but I just wanted you all to know I appreciate it. So thanks for being here. A little extra. Anyway. We're on the last chapter of Chemistry 223, which is crazy that it is down to the last chapter. We don't have that many lectures left, to be honest. But this lecture is the one that, first of all, is very near and dear to my heart, which I'm going to talk about why. And the second thing is this is the lecture, this is the chapter that I've had the most positive feedback from students that went on after Chem 223 of all the chapters. So I think it's really important. It's the last chapter, it's true, but what it's going to do, it's just going to give you a heads up if and when you take organic chemistry. All right. Now, organic chemistry is the second year chemistry class if you are a chemistry major, stuff like that. And I know that not all of you maybe will take organic chemistry, and that's fantastic too. If you are going to take organic chemistry, here's my personal story. I did pretty well in my equivalent of Chem 221 through Chem 223. So when I waltzed into organic chemistry, I was like, oh yeah, I'm a bad A and stuff like that. I'll have no problem. Snowed over. I was so blown away. My grade, needless to say, went down a little bit. Anyway, and the problem is I had no idea how organic chemistry was organized. It was quite different from what we've been doing so far and from my previous classes that I had taken. They have in organic chemistry what's called classes of organic chemicals. And there's different names and all these different classes, and I thought that certain compounds were different from what they were said. I had an instructor who had a little bit of an accent, so this was probably a little bit on me too. But anyway, some compounds were very similar, and yet I was not getting the big picture. So man, oh man, when I became an instructor, I said, I do not want my students to go through that experience. I want it to be a positive thing. I want you to have a heads up as to what you're getting into so that you'll be definitely more prepared than I was. So anyway, students have taken, I've had in the past, and they went on to take organic chemistry, and they're very thankful usually, at least that's what they tell me anyway, okay, because they do understand a little bit of what's happening before they get into it, and you won't have this like overwhelming kind of feeling and stuff that I had, like, oh my gosh, I don't know if chemistry is for me kind of thing. So that's kind of the big picture here. Now, if you're not taking organic chemistry, don't despair. There's uses for this as well, all right? If you walk down Fred Meyer's or Home Depot, these kind of places, there's a lot of chemicals on there, and you'll start to recognize now some of the names. Pharmaceuticals, they usually give you like a piece of paper which has all the chemical names for things. You'll start to recognize now some of the pieces that are in the pharmaceuticals that you might get. So it is useful even if you're not going to take organic chemistry, but boy, if you do, I sure am going to try and do everything I can to help you avoid the pitfalls that I fell into. Now, organic chemistry, a year-long class, and there's no way in a couple of lectures I'm going to do justice to it, all right? So we're going to kind of pick and choose our battles in this section. We're going to look mostly at what's called nomenclature of organic chemistry, the naming, okay? Another huge part of organic chemistry is the reactivity, how you make these things and what you can do once you have them. I'm going to show you just a couple of examples, but honestly, that's more for the full year class than what we're going to do. Also, some organic chemical families are more common and used more than others. So for example, we're going to get to some names called esters and amides, and I encourage you to check it out, but really I'm not going to ask you anything on it. I just want you to hear these names, all right? Amide is different from amine, and ester is different from ether. So right away, that's one goal I want you to hear, because those are different things. They're not the same things, as I found out on a quiz. And let's say we didn't have Lois quizzes either. But anyway, so I'm already trying to share with you some things to kind of get you up to speed. Should be cool. Questions on any of that? So organic chemistry is more or less just the chemistry of the nonmetals, carbon, hydrogen, oxygen, nitrogen, a couple other things, sometimes metals, but it's mostly organic, mostly the nonmetals, especially things around carbon. And it might seem kind of silly because the periodic table has almost more than 100 elements, but really most of the compounds that are known are based on carbon, all right? So carbon is huge, all right? Some compounds, like this one right here, this is propane. So this weekend, if you have a barbecue or something like that, you'll probably be using propane as your fuel source. On the other hand, some of these compounds like benzene, this compound is informally known as propellerane. Lots of these different things are variations around there. Carbon is so flexible when it comes to making bonds. And if you remember back from Chem 221, when we talked about Lewis structures and Vesper, carbon can make up to 4 bonds, and so that's as many bonds as it makes, but it can make double bonds and single bonds, and it makes lots and lots of different combinations. So carbon is amazingly flexible when it comes to making compounds, and that's one of the reasons why organic chemistry is big. Organic chemistry used to be known as the chemistry of life, but that's kind of passé now because biochemistry, which is where biology and chemistry has kind of usurped that. But organic chemistry is still very involved with the things we use in life. So caffeine and DNA and stuff, they all have carbon in them. Pretty important stuff. So in the full year chemistry class, all right, what they usually will do is they'll first talk about how to name the compounds, the nomenclature of organic chemistry. And that's what we're going to focus on mostly in this class, all right? We're going to look at the naming of the most common things so you can kind of hear what they are and kind of see what's happening. Most of organic chemistry, though, is on reactivity, how you make the compounds, what you can do once you have them. I'll show you a couple of examples, but this is going to be by far an area where the full year chemistry course will knock it out. So, again, we're going to focus more on the naming, more on the naming than the reactions, but it will hopefully then give you a good head up as to what you're getting into if you take the full course. So carbon, so versatile, all right? In organic chemistry, there's so much carbon that there's many different ways to represent it, all right? Now, if you remember from Chem 221, when we talked about carbon, carbon likes to have 4 bonds. And when you have 4 bonds, to keep those electrons as far apart from each other as you can, you don't want to have 90 and 180 degree angles usually. But what you do have is tetrahedrons. Tetrahedral angles are about 109 degrees. However, when you're talking to each other about organic chemicals, a lot of times people will write carbons in a straight line like that. They call them carbon skeletons, all right? Now, you as the hip chemist need to realize that in reality, these aren't 180-degree bonds. They're going to be about 109, which is what we're seeing right there. And these bonds will rotate, all right? So you can have them twist around and stuff like that. If you see like a kind of an upside down T, that's the same as a regular T, but again, they're all about 109-degree angles usually. So in your mind, just realize that you have to be kind of flexible in terms of how these things are written. And the bond angles honestly will usually be tetrahedral 109, but you can rotate them around like crazy if you need to. Now, if that wasn't weird enough, hydrogen is everywhere in organic chemistry. And hydrogen honestly isn't really that exciting. So instead of writing carbon, 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 remember in the back of your mind, carbon likes to have 4 bonds. So this carbon is connected to one carbon, that's one of the 3 bonds. The other 3 bonds around it will be hydrogen, all right? So instead of writing CCCC, we really could write CH3, CH2, CH2, CH3, because carbon has to have 4 bonds. That's an underlying rule of organic chemistry. Now, writing this out is great, but in reality, remember, these are all tetrahedral carbons usually. So the angles are really more like 109, but it's hard to write it that way. Now, if you have Microsoft Word or something like that, and you have access to subscripts, you can write CH3, CH2, CH2, CH3, which is cool. But this is another way to write these crazy chemicals. So notice here, this is what they call the carbon skeleton formula. Each vertex is a carbon. So this on the end is CH3. In the middle right there, that's a CH2. This is CH2 and CH3. If you get used to this way of writing things, it's very easy to write. You can write them very quickly. You can quickly express the kind of things you're going to get across to. But in reality, just realize the molecules are much more complex. Here's a double bond right here. So notice that there's 2 lines instead of just 1 line between those carbons. Here's a triple bond, all right? 1, 2, 3 lines between the carbons. And of course, in the back of your mind, remember that in reality, the orbitals of the different atoms, they kind of mesh together, and it's the overlap that creates like bonds like this. So really, we should be writing in the space-filling models, but those are super ugly and hard to realize what's going on. In Chem 221, every carbon with just single bonds around it, tetrahedral, all right? So like that carbon right there has 1, 2, 3, 4 bonds, that's tetrahedral. The double bonds, if you remember, were trigonal planar. So there's 2 hydrogens and a double bond, that would be a flat part. And the triple bonds were linear, all right? So you can see even from the space-filling model, this is like straight across, that's the 180-degree angles. So, we haven't talked about Lewis structures and stuff for a while, but it will be important in this section. Any questions on any of this? All right. These line formulas or skeleton formulas are used a lot in organic chemistry. I just want to introduce them here so that you see what's going on. At first, when I saw these, I thought they were like Egyptian hieroglyphics or something. I had no idea. So this was one of the things that I wish someone would have kind of expressed to me a little closer than they did. So carbon is king. Lots of different ways to write it. Again, you could write these straight across, you can bend them, stuff like that. They're all the same things, and you can see what they really look like over here. Chemistry, in organic chemistry, is built on smaller pieces that combine to make bigger molecules. And if you've ever done like Lego sets, all right, like you get these elaborate Lego pieces, like hundreds, thousands, whatever of them, right? But you put them together to make cooler pieces, all right? Cooler spaceships or whatever you're making Legos with. Alkyl groups are kind of like the small pieces of the Lego. They're not really very exciting. Alkyl groups are not compounds, all right? But chemists use the idea of the alkyl group to understand how compounds are made. Excuse me. So alkyl groups are usually sp3 hybridized carbons. Now sp3 is really just a fancy way to say tetrahedral. So if you see sp3, that means that it's a tetrahedral carbon. Now, the alkyl group names are super important in organic chemistry, which was one of the things I wish someone would have told me. A methyl group is a CH3. Now, if you think about this CH3, carbon likes to have 4 bonds, all right? So CH3 means that 3 of those bonds are being taken up by hydrogen. But there's like a 4th bond, a 4th connection point that you can have to the CH3. So remembering again that carbon likes to have 4 bonds and hydrogen can certainly only have 1 bond. 3 hydrogen bonds and 1 bond left to do something else. So that's why it's not a compound unto itself. It's like a building block for other pieces. If you take that CH3 carbon and you add a second CH3 carbon to it, it creates what's called the ethyl group. So the methyl group was essentially a CH3. It had a carbon that's sp3 tetrahedral, but there's 1 spot missing. An ethyl group is when you add another sp3 hybridized carbon to the end of the methyl group. So an ethyl group, everything's tetrahedral, everything's sp3, but there's still like a spot to put something in there. So methyl groups have 1 carbon, ethyl groups have 2 carbons. And if you have a propyl group, you would add another sp3 CH2 group to the end of it. So methyl, ethyl, propyl. The next one is butyl. All right. Butyl is when you'd add even yet another CH2 group on the end of it. By the way, propyl maybe sounds a little bit to you like propane, or methyl like methane. That's not an accident, that's intentional. We'll talk about that here in a little bit. But these are literally the building blocks of all organic chemistry. Pentyl would be 5 carbons in a row. Hexyl would be 6 carbons, heptyl 7, octyl 8, etc., etc. And a lot of times what people will do is they'll just write big R for some kind of generic alkyl group. Now, big R is used a lot in chemistry. It's the gas constant, 8.3145 or 0.082057. R is also sometimes used with linear regression for the crazy correlation coefficient. This is yet another use of capital R. Oh joy. But anyway, in organic chemistry context, R could just mean any of the alkyl groups. So maybe you'd have a heptyl group or a methyl group, some random alkyl group is in there. At this point, I need to advertise one of the handouts that's in the companion and online. It's called the Organic Chemistry Nomenclature Guide. And in this guide, I start off by listing some of the alkyl groups, and then I go through the different families we're going to talk about here in a little bit. So while you're learning organic chemistry, I do encourage you to check out this nomenclature guide. If you can't find it online, I'll send you a link and stuff. Yeah.
So would it be then common with good practice then to do capital R with subscript like M to represent methyl, or is it just that that's a stand-in in general?
Good, excellent question. They don't usually do that, but here's how it could be used. We're going to see here in a little bit that if you take the alkyl group R and you put an H next to it, that makes what's called an alkane, all right? So you could take a methyl group and connect it to a hydrogen. That would be an example of an alkane. But you could also take, say, the butyl group and put a hydrogen next to it, and that would be an alkane. So it just is a way to represent like any of these and stuff on there, if that makes sense. I'll show some examples here. That's the big question. Please ask any questions that come to your mind. This is the time to ask. Again, like I said, I don't want you to fall in the rabbit hole that I definitely fell in, so. Okay, so alkyl groups, building blocks, but not compounds themselves. But we're going to see these names a lot here coming up. Just remember methyl 1 carbon, ethyl 2, propyl 3, etc., etc. So, a hydrocarbon is a compound that has only carbon and hydrogen in it. And there are several types of hydrocarbons, but we're going to start off by looking at what's called an alkane, which is what I mentioned to Ryan just a second ago. Alkanes now are true compounds, all right? These are things that you can put in a bottle or whatever and sell to friends or whatever. And the simplest of the alkanes is actually something we've used several times in Chemistry 221 through Chemistry 223. So if you take one of those alkyl groups, like the methyl group, and you put a hydrogen on the end of it, that's what an alkane is. And if you take a methyl group and put a hydrogen on the end of it, it's called methane. And natural gas, which you might have used at home, and we definitely use for Bunsen burners here at lab, natural gas is basically methane. All right, it's a big source of methane. It's a good flammable source and stuff like that. It's great. But there's more than just methane. We'll talk about that. So if you have an alkane, it's just an alkyl group with a hydrogen on the end of it. Remember, carbon must have 4 bonds. So if I take this ethyl group, which I have up here, and I put a hydrogen on the end of it, it becomes an alkane. I took an ethyl group, and I added a hydrogen to make it an alkane. So to name what this thing is, if you look right here, you're going to take the YL off the alkyl group. So ethyl becomes F. You add ANE to it. I guess I should have put plus ANE. This thing right here is ethane. A methyl group, you take the YL off the methyl, make it meth. Not that kind of meth. Anyway, meth plus ane is where methane would come from. And again, these are formula, these are compounds now. So here's our CH3 with the hydrogen. This is methane, all right? And again, to do that, methyl minus YL plus ANE, methane. All of the alkanes have a predictable formula. For every N hydrogens, you're going to have 2N plus 2 hydrogens. So let's check this out. Here's methane. It has 1 carbon, so N is 1. 2 times 1 plus 2, 4 hydrogens. Over here on the board, I wrote ethane. It has 2 carbons, so N is 2. 2 times 2, 4 plus 2, 1, 2, 3, 4, 5, 6 hydrogens. All alkanes follow this formula. So one day Savannah's working on a new compound and she has some kind of C7H16 compound, which I have no idea, but for every N carbons, there were 2 times 7 plus 2, 16 hydrogens, some kind of an alkane, right? And that's kind of useful. All alkanes kind of react the same, so that's kind of a cool thing. Questions on that? Okay. Ethyl plus a hydrogen becomes an alkane. You take that one spot and you just plug it up with hydrogen. So ethyl plus H, take off the YL, add ANE, it becomes ethane. And the one that we'll use for barbecuing, if barbecuing is your jam, propyl group, which is 3 carbons plus a hydrogen, becomes a compound. It becomes propane. You take the YL off the propyl, add ANE, propane. So methane, ethane, and propane are all alkanes. All right, they're all great. Alkanes are great fuel sources, all right? All of them are great. Octane is gasoline, basically, which if you took a gasoline-powered car here to school today, then yeah, you used octane. Propane is, again, for barbecuing most of the time. Butane is in cigarette lighters. So there's lots and lots of uses for these as fuels, all right? There's not a lot of else you can do with them, to be honest, but as fuels, they can be pretty cool. And again, if you had 10 carbons, 10 times 2, 20 plus 2, you'd have 22 hydrogens if it's an alkane. Questions? Yeah, right.
So none of these can be like liquids or gases. Can they be solids as well?
Yes. If the molar mass gets big enough, then it takes too much energy to get it into the liquid phase. So yeah, if you get up to, I think, don't quote me on this, but I think it's like 20 carbons, you can actually have solid state fuels, absolutely. And of course, if you freeze them down, Ryan, you can make any of these solids as well. Methane, right there, is usually just a gas. I believe when you get to pentane, they begin to get liquids, and then it's sometime after that you turn into solids. Yeah, great question. Questions? All right. Now, one weird thing, though, happens when you get to the next alkane. So we saw methane, ethane, and propane from the ethyl, methyl, and propyl alkyl groups. The butyl group is 4 carbons. You put a hydrogen on the end, it becomes an alkane. The name of it would be butane. So here's CH3, CH2, CH2, CH3, everything tetrahedral, no problem. However, if you remember back to the Lewis Structures lab, one of the things we focused on were isomers. And an isomer is when you have a formula, but you can write it in different ways. So one thing that happens in organic chemistry is that you don't always have a nice long chain of carbon atoms. Like this one would have 4 carbons like in a long line in a chain. But sometimes what happens is you could take off, say, this CH3 group right here and put it where this hydrogen is, and then this hydrogen would connect to the outside carbon. So this compound right here is an isomer of butane, all right? And it's the same formula, C4H10, but it's not the same compound. This compound is going to have different polarity than this compound will right here. When you start bending the carbons around, getting them in different configurations, it's going to be harder to know which side then is more polar, which side is more non-polar. This side is less polar than this one, I would argue, but honestly, sometimes it's hard to say what's going on here. So if you have an isomer of alkane, it is a different compound. Same formula, but you're going to have different properties, different boiling points, melting points, whatever. So chemists need to be able to name this crazy thing. So one of the things we're going to focus on here this morning is how the longest chain is critical when you name compounds. So let's look at this compound right here, all right? If I put my pencil down here and I want to try and circle as many carbons as I can, but I can't go backwards and I can't pick my pencil up, I can go 1, 2, 3 carbons, but then if I can't go backwards and I can't pick my pencil up, I have to stop. Maybe Daria would go 1, 2, 3 carbons like that. Cool, but then she has to stop. Maybe Jane would start here, which is fine, and go 1, 2, 3. But then we all have to stop, all right? So in this compound here, the longest chain, regardless of where you start, is going to be 3 carbons. You might do it here, here, or there. Doesn't matter, 3 carbons. Now, let's pretend that these are our 3 carbons. One of the carbons is not part of the longest chain. So this compound, you can see how the base name is 3 carbons long, which would be propane. But it's not like the propane I showed on the last example where there was a hydrogen right there. There's a methyl group, a CH3 on it. So this compound is a methyl propane. The longest chain is what you named last, propane. A methyl group is not part of that longest chain. And I'll put a 2 right there just to show that it's off the second carbon. So what we're going to do now is we're going to kind of break away a little bit from our alkane discussion and start thinking about how to name these compounds. And the punchline here is you look for longest chain and smallest number. I'll talk about smallest number here in a little bit. But for right now, just realize that, oh yeah, isomers become an issue in organic chemistry very quickly, all right? In 4 carbons, you can have 2 different versions of it. So this is why it becomes kind of important. Any questions? Okay, but first, let's just go back a second. Here's 5 different compounds, and the question is, which one of those could be an alkane? Now, if it's an alkane, for every N hydrogens, you're going to have 2N plus 2 hydrogen. N carbons, you'll have 2N plus 2 hydrogens. So, for example, this first one right here, C2H4, it has 2 carbons, so N would be 2. If it's an alkane, it would have 2 times 2 plus 2, 6 hydrogens. This doesn't have 6 hydrogens, so that is not an alkane. Could this one be an alkane? Nope. Every N carbons here, there are 2N hydrogens in this formula. Like you have twice as many hydrogens, but you need that extra plus 2 to make it an alkane. So this is not an alkane either. However, this one, if N is 14, then 2 times 14, 28 plus 2, sure enough, 30 hydrogens, that one is probably an alkane, all right? This doesn't have the right formula. This has oxygen. Alkanes don't have any oxygen, so those are all out. But answer C there, that one could be an alkane. And as an organic chemist, that's kind of cool to know, because that might be a good like fuel to use, but there's not going to be a lot of other things you can do with it reactivity-wise. Any questions on that? Okay. So, all the alkanes, like I said, some kind of alkyl group with a hydrogen. This is CH3 methyl plus hydrogen makes methane. As a full Lewis structure, you'd write it CH4 like that. You don't have a line structure. But when you have 2 carbons, this would be ethane. It's an ethyl group plus a hydrogen, CH3, CH3. You can just write it as a line. Now, this is that weird line structure once again. Every vertice is a carbon, all right? It shows the carbon-carbon bonds, but it doesn't show the carbon-hydrogen bonds. So you as the hip chemist then know this is carbon and this is carbon. This carbon will have 3 bonds to hydrogen. Carbon must have 4 bonds around it, all right? And you can see here propane would be like a triangle, like a little, that's not a carrot, I think is the carrot. Anyway, carbon, carbon, carbon. This carbon would have 2 hydrogens. The N carbons would have 3 hydrogens, stuff like that. But again, once you start getting to the more complicated alkanes like butane, then you can have different isomers. This compound right here is just regular butane. Sometimes it gets an N in front of it, N-butane. You could write it in line structure 1, 2, 3, 4. This compound right here, which is technically methylpropane, we'll talk more about it, you have 1, 2, 3, 4 carbons, but they're different orientations in space. But all of these are alkanes, all right? That's the important part to get across. Okay. All right. Now, here are the isomers of pentane. So when you have all the carbons in a long chain or long line like that, sometimes they'll put an N in front of it. So this thing here would be a pentane. It's technically N-pentane. Down here, you've taken off the CH3 on the end and put it on one of the middle carbons. So again, remembering that you're trying to find the longest chain of carbon atoms, 1, 2, 3, 4, but then you have to stop. 1, 2, 3, 4, then you have to stop. Now you could go in this one, 1, 2, 3, chemists like longest chain of carbon atoms, all right? So 1, 2, 3 would not be cool in organic chemistry, all right? Longest chain of carbon atoms is the way to go. So regardless of which direction you go, you're going to get 4 carbons. That would be a butane, all right? Another thing that I talked about earlier is smallest number, all right? And this is another big thing about organic chemistry. This methyl group is not part of the longest chain. So if you start with left to right numbering, 1, 2, 3, 4, you could call this compound 3-methylbutane. Okay? However, if you start on the right side and move left, 1, 2, 3, 4, you could also call it 2-methylbutane. And believe it or not, this is important in organic chemistry. Smallest number, always the way to go. So this compound is best called 2-methylbutane. If you say to your instructor, I got some 3-methylbutane, it sounded kind of like you're a hick, all right? And like, I ain't knowing what you're talking about. I can understand what you're saying, but I want you to be cool when you get your PhDs from MIT or whatever. So smallest number is the way to go, all right? Don't use the bigger numbers and stuff like that. We'll talk more about smallest numbers and longest chains. Any questions on why this compound is 2-methyl? Cool. Also realize that sometimes the molecules themselves will not really align themselves with our English way of thinking about things where everything is left to right, all right? Like it feels like 1, 2, 3, 4. It should be 3-methylbutane. Well, in chemistry, everything rotates like crazy. As long as you're above absolute zero, these things are going to rotate like crazy. So what would be looking like 3 initially will rotate around, so it's 2. So it's really important for you as the student then to, in your mind, like rotate things around, all right? And see what the smallest number is, because that's really important in organic chemistry. All right. The other isomer that's possible is if you take, if you will, a methyl group off both ends and put them on the middle carbon. Now in this molecule, 1, 2, 3 carbons, that's as long of a chain as you can get. 1, 2, 3, 1, 2, 3. Any direction you go, you're going to get a propane. Propane is 3 carbons. And you have 1, 2 methyls not on the longest chain. So notice this nomenclature, 2,2-dimethylpropane. Dimethyl means 2 methyl groups, and they're both off the second carbon. All right, that'll be important as we get to some longer structures here in a little bit. But all right, Prof hat off. I'm an inorganic chemist. I'm a metal guy. Yeah. Oh, not that kind of metal. Sorry. Well, maybe it is actually. But anyway, remember that organic chemistry, these are just the rules that they use. They're really weird. But there's also no dumb questions. So if you think of anything you want to ask, this is the time. All right. I have no axe to grind. I'm on your side. I would rather talk about coordination chemistry, honestly. All right. Prof hat back on. Any questions?
Hexane is a covalently bonded molecule consisting of 6 carbon atoms and 14 hydrogen atoms. Each hydrogen atom forms 1 covalent bond, and each carbon atom forms 4 covalent bonds. These 20 atoms can be rearranged into 5 different compounds called structural isomers, each having slightly different properties. Notice how the boiling points of each isomer changes. Arranging the carbon atoms in a straight chain produces N-hexane. Moving the end carbon to the second carbon position and rearranging hydrogens produces 2-methylpentane. Sliding the methyl group to the third carbon position produces 3-methylpentane. Moving the methyl group to the fourth carbon position appears to make 4-methylpentane. But wait, rotating the molecule shows that it's identical to 2-methylpentane. Now, adding the end carbon to the second carbon position produces 2,3-dimethylbutane. Moving the methyl group to the second carbon position produces 2,2-dimethylbutane. Sliding both methyl groups to the third carbon position appears to make 3,3-dimethylbutane. But wait again. Rotating the molecule shows it's identical to 2,2-dimethylbutane. These are the 5 isomers of hexane.
Okay, so 4 carbons had 2 isomers, 5 carbons had 3, 6 carbons looks like 5. It gets more and more and more as you get bigger and bigger. So isomers are big time important in organic chemistry. I like this video because in the upper corner it showed the different boiling points of these compounds, and they did vary quite a bit. So the differences in polarity by having methyl groups or dimethyl groups versus long chains becomes really important, all right? And this is also why there's just so many incredible number of organic chemicals out there, because carbon's really flexible and stuff, and you can do it. So let's go back again and do some more examples of this longest chain, smallest number thing, because this is really important. So let's say you had this molecule right here, and you said, what is the name of it? Well, you always want to find the longest chain of carbon atoms. And again, you can think about these chains in any way you want, but it's basically like putting your pencil down and circling as many carbons as you can. So you could, for example, go 1, 2, 3. That could be your longest chain, but that's not cool in organic chemistry. You want to put as many carbons into that base part as you can. So if you do all of these, you get 6 carbons. That's a lot better than having just 3 carbons, all right? It doesn't really matter if you circle this CH3 or if you circle this CH3 and add this one outside. A lot of times there's going to be more than one way to find the number of them, and either way is fantastic. So when you name these things, the longest chain, 1, 2, 3, 4, 5, 6, you name it as if it was an alkane by itself, all right? So 6 carbons would be hexane. This would be 6 carbons. 6 carbons is hexane. There's a methyl group not in that longest chain. And again, it doesn't matter if you circled this one or this one. One of the methyl groups isn't going to be in your chain. The smallest number is really important. So let's say we started down here at number 1. 1, 2, 3, 4, 5, 6. This could be a 5-methyl hexane. All right. But organic chemists love to have the smallest numbers possible. So it's, especially when you're learning, I recommend that you number them in both directions. So earlier I went 1, 2, 3, 4, 5, 6, could be 5-methylhexane. But as you can see, it's better to start up here, 1, 2, 3, 4, 5, 6. So this could be 2-methylhexane or 5-methylhexane. You always pick the smallest number possible, all right? So 2-methylhexane would definitely be the best name for all of these things that are there. So find the longest chain, number it from both sides when you're learning. You want to get the smallest number of your substituents. So methyl group would be just 2 here. Sometimes you'll have ethyl groups, propyl groups, butyl groups, stuff like that. All of these things would be possible. But again, you want to try and fit as many carbons in your longest chain as you can. It makes the name simpler, honestly. So, questions on that? Okay. Here's another example. Now again, lots more carbons. You know, when you start getting to DNA, man, you start getting hypnotized, but no. So let's figure out how we would name this crazy thing. All right. So again, lots and lots of carbons, but you want the longest number of carbons possible. So you could go, for example, 1, 2, 3, 4, 5. That's 5 carbons, and that's not bad. You could go 1, 2, 3, 4, 5, 6. 6 carbons, not too shabby. However, the best you can get, as you can see, is if you circle these right here, 7 carbons. All right? So try to fit as many carbons in your longest chain as you can. 7 is a heptane if it was an alkane. And notice how it was circled there. I would recommend circling them when you're learning them because you can kind of see which carbons are part of the chain and then which carbons are not part of the chain. So in this 7-carbon chain, we have 1, 2, 3 methyl groups that aren't in the chain. And we also have an ethyl group, which is not in the chain. So again, chemists love to alphabetize. Ethyl comes before methyl. So the ethyl is listed first, and the methyl, trimethyl in this case, but focus on the methyl is afterwards, Gesundheit. So the ethyl is first, the methyl is after that, and the heptane at the end. But we have to tell the other chemists where those methyl groups and ethyl groups are. This is where, again, numbering in both directions is really, really cool. Let's say we started up here. 1, 2, 3, 4, 5, 6. So if we started up here, we would have 3, 4, 6 for trimethyl. And we would have 1, 2, 3. We would have 4 ethyl. So that could be 4 methyl, 3, 4, 6, whatever it was, trimethyl heptane. However, number in both directions. So starting here, methyl at 2, ethyl at 3, methyl at 4, and methyl at 5. 2, 4, 5 are smaller numbers than the numbers we had before. And 3 is smaller than the 4 ethyl we had before. Smallest numbers always win, all right? Again, I think it's more just, it makes it easier to understand. Smaller numbers, longest chain. Start off by writing the atoms together in the chain. You can fill in the pieces from there. Any questions? Okay. So let's say I said, what's the name of this compound, all right? First of all, as we're going to see, it's helpful to think about what kind of compound it is. But all the carbons here have single bonds. They have connections to hydrogens. This is an alkane, all right? It's not so important yet, but it will be eventually. So this is an alkane. If we had all of the carbons in a line, it would make it really easy. There's 6 carbons total, but this is not a hexane because the 6 carbons are not like all together. So what you can do is figure out what the longest chain is. 1, 2, 3 could be a propane. Because longest carbon atoms, longest chain is what you want. 1, 2, 3, 4 is how I would look at it, but you could also go 1, 2, 3, 4, 1, 2, 3, 4, or 1, 2, 3, 4, whatever, all right? So 4 carbons is the longest chain of carbons you can have, and that's going to be a butane. So our answer here is going to be A, B, or C. The 4 carbons in a row would be butane. Is that cool? Everybody cool with that part? Okay. Let's pretend that this is our longest chain. All right, these 4 carbons right here. 1, 2, 3. 2 methyls are off the 3rd carbon. We could call this 3,3-dimethyl to show there's 2 methyls. Butane, 3,3-dimethyl-butane. What? Good. I see some doubting Thomases here. Well done. Yeah, count from both sides, man. 1, 2, 3 would be left to right. In good old English language, that's how it rolls. However, count right to left because these things rotate. 1, 2, 3, 4. This could also be 2,2-dimethylbutane. And the smallest numbers always win. So 2,2-dimethylbutane would be the best name for this compound. Butane would be 4 carbons in a row. Dimethyl, 2 CH3s, each of them off the 2nd carbon. Good to go. Any questions? Here's another example, how to go from a name to a structure, all right? This compound is 2,2,4-trimethylpentane. And what I recommend, if you're going to do this, is you start on the very end, on the pentane part. How many carbons in pentane? 5, right on. So what I would do is just write 5 carbons in a row. Carbon, 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 carbon. All right? After that, we have 3 methyl groups, 3 CH3 groups. And those 2, 2, and 4, those numbers tell you where the methyl groups are going to go. So what you can do if you want to just use carbons is you'd have a CH3 and a CH3 off the 2. That's the 2, 2 part. The 4th one will also have a CH3 group off of it. So there's the carbon backbone. If you want to fill in the rest of the carbons, that's awesome. Honestly, you could just keep it like that if you want. All right. But notice how, again, we started at the end and then kind of worked our way to the left. That's the way to knock these structures out from the names. Pretty chill. So, cool. Any questions on that? All right, we're going to take up more of this, not on Monday because that's Memorial Day. Woo-hoo, everybody stay home. But on Wednesday of next week, we'll do more of this stuff. I sure appreciate you all being here. Have a wonderful weekend.